In this video, we're going to be kind of putting a lot of different concepts all together. In fact, some concepts that we studied way back in September, October, together with some concepts that we're studying now. So it's kind of a neat lesson. In fact, we are almost here at the final part of Chapter 2, finishing up limits, continuity, asymptotes, and so we're going to kind of put it all together over this next week and then test the following week, and then we'll be done with Chapter 2 and on to derivatives. But for the time being, just wanted to review the continuity concept here. The formal definition of continuity is basically a function f of x is said to be continuous at x equals c as long as the limit as x approaches c of f of x is equal to the function at c, so the value of the function at c. So keeping in mind, we talked a little bit about the three criteria that must be met. F of c must exist, the limit must exist, and then they have to be equal to one another. So first scenario here is where the limit does exist, where the limit is equal to whatever that y value is of the whole. Here we have the limit not existing, but f of c existing. So the value of the function is right there where the solid circle is above where c is. And then if we wanted to make sure that the limit was the same as the value of the function, plugging the hole basically is how we find that f of x is continuous here at c. Okay, so there's a couple things down here that we've already done. We did this stuff right here back in the pre-calc part. So the first semester we found the coordinates of the hole, we found vertical asymptotes, and we found horizontal asymptotes. So I want to tie in limits with that. And in order to tie limits into that, we have to figure out what was the definition of a vertical asymptote. So we couldn't talk about this because you didn't know what limits were back in the first semester. So a vertical asymptote would be where either the limit as x approaches a from the right is equal to either positive or negative infinity, or x approaches a from the left is positive or negative infinity. If either one of these cases is true, then the line, the vertical line, x equals a, is a vertical asymptote. Okay? So we can keep that in mind. And then the horizontal asymptote, if you're asked the definition, then you would see here that as x approaches infinity now, when x approaches infinity, if you get a limit, a real number less than infinity, so it could be a negative number, it could be a positive number, it could be 0. As long as you get a real number and you don't get infinity, then you have, so if x approaches infinity or negative infinity and you get that real number, then that line y equals L is the horizontal asymptote. Okay, so that's a little background, so 3 minutes of background, and let's go ahead and do some problems. Alright, find all holes, horizontal asymptotes, and vertical asymptotes. Well, again, we've done this. Remember, x equals 2 is a discontinuity. Okay, so we have discontinuous at x equals 2, and then because you can't plug 2 in. Now, can you factor the numerator? No. So therefore, we have a vertical asymptote at x equals 2 because you can't factor and then cancel that particular fact. You can't factor the numerator and then cancel whatever you get up there with this x minus 2. So x equals 2 is the vertical asymptote. Okay. Well, we also talked about the bubble concept in terms of horizontal asymptotes. Okay. And the horizontal asymptote, you knew the bubble concept way back when, but now we can tie in the limits, and that's really why we get this bubble concept, or where we get it from. The limit is 2x, the limit as x approaches infinity of 2x plus 3 over x minus 2. We can see we have same size bubble, and we just get 2. That's a real number less than infinity, therefore the horizontal asymptote is y is equal to 2. Okay, and we should be able to see here that since we have only one discontinuity at x equals 2, it means that that discontinuity represents a vertical asymptote. We have no hole at x equals 2. We have that vertical asymptote. Okay, let's see. Number 4 looks a little bit more challenging than number 2. So let's go ahead and do number 4 because it's got that cube root in there. So what we did early on in the semester, the first semester, was we factored the numerator. Take an x out and we get x squared minus 4. And we can take an x out of the denominator as well, factor out the GCF, and we get x squared plus 5x plus 6. Well, hopefully we can see we can continue to factor here. I need to move this over a little bit. We can factor that difference of squares. X squared minus 4 is x plus 2 times x minus 2. And then we can see we can FOIL this here, x plus 3 and x plus 2. And a little kind of trick of the trade here, if you get stuck, look at the other factors, and more than likely one of the above factors is going to be one of the factors down here, which is just the case that we just found. So we saw that we canceled the x. So if you remember that story I used to tell where all numbers want to be vertical asymptotes, well, the ones that get canceled go to the whole. So we see that the wholes would occur when x is equal to the discontinuities. We should probably talk about the discontinuities first, but we have a discontinuity at 0, -3, and -2. Whatever x value, whatever real number makes the denominator 0 is a discontinuity, and those discontinuities are the only ones that could potentially be the vertical asymptotes. So once we cancel them, though, we see that they only are wholes. So we have x equals 0 and x equals -2. Okay, again, I'm going a little bit quick through this because we've already done this stuff. Vertical asymptote, on the other hand, x equals -3. Okay, in the horizontal asymptote, we take the limit as x approaches infinity, and we see that we have same size bubble, and we get a limit of 1. We can talk about limits now when we discuss asymptotes. Now, all it asks us is to find the wholes, horizontal asymptotes and vertical asymptotes, but for number 4 here, since we do have a whole, we want to figure out, well, what is the y coordinate of the whole? Well, to find the y coordinate of the whole, all we have to do is take the limit. Okay, so the limit as x approaches 0 of this function. And you know what I'm going to do? Instead of writing this whole function y, I'm going to just go ahead and rewrite the reduced version, the stripped down version of the original function. So the stripped down version is when we factor and cancel, we get this function here. And so all we have to do is replace x with 0. We get -2 over 3. And therefore we get one whole at the x coordinate of 0 and the y coordinate of -2/3. Okay, let's find the y coordinate of the other whole. Maybe pause the video and try this one on your own. The limit as x approaches -2 of x minus 2 over x plus 3. Plug a -2 in for x. We get -2 minus 2 is -4. -2 plus 3 is 1. So we get -4. So we get a whole, another whole, at -2, -4. So did we figure everything out? We've got the coordinates of the wholes, we've got the horizontal asymptote, and we have the vertical asymptote. So I think, you know what, number 5 would be worthwhile to do, but I'd like you guys to try that one on your own. Yeah, try that one on your own. In fact, try numbers 2, 3, and 4 on your own and bring that work into class on Monday.